just remove the back effects so that it's a little bit more visible. Is a printed circuit board that I designed when I was studying, or I made when I was studying. It is all basically based around this microcontroller. In this case, it's a PIC. I can't even read the writing anymore, but it's a microcontroller, and we wanted to have what we call a breakout board, meaning that it's got these connectors which you can connect to the board. It's got some lights. I think it's got a real-time clock on there and a battery backup. And we just wanted to create our own little board for us to use. Now, a couple of mistakes that I have made. Now, it does have a name on this board, but I do not know which revision the board is, because we did create a couple of these boards because we made the first ones, realized it doesn't work, and then we revised the board. A couple elements that I want to highlight and specifically show you is that for this board as well, I had to solder everything on there myself. And that is specifically what I want to look at today, is that you will have to, when you are creating these boards, you will have to, once they are created, to inspect them. You have to visually inspect them, look at all of the soldering elements, if they are soldered on correctly, if the joints are correct. And I'll just want to just to have a look at it beneath the microscope, and hopefully I can tell you a short story about why it looks like that. Right, so you should not be seeing anything right now. I'm just trying to place the board in such a way that we can have a look at. I think it's just, give me a second. Right, I'm should be sharing my screen with you. Let's do a little bit of focus. Right. Now, please remember, last time when we tried using this camera, I lost audio. So if I lose audio once again, just let me know, and hopefully I can fix it. Right, so I'm sharing my screen. Right, so this is a close-up of my specific board. Now, these are all soldering joints which I made myself. Let's see if I can create the... Right, that is probably as good as it's gonna get. Now, specifically, I would like to, this does not work so well. This camera is not very good. Right, so these joints are what I made myself. And a couple of things now looking back on it is a little bit weird. So this is this top left joint is probably the one I made first, and is one of the better looking joints. So these joints I can see they look really good. How do I know they look good or they are successful soldering joints? Well, I can see that the soldering liquid or the soldering metal has fully melted and makes good contact with the trace. The pad is almost fully covered in soldering iron, and also the component, which is the through-hole component sticking out, is almost fully covered in solder. I cannot see any cracks or any lifting of the board. So these soldering joints are good. And you can see I probably did this in order, starting from this one This one was for my first one, second, third, fourth. And as you might see, they look like they get a little bit worse. So ending up at this joint here at the bottom, well, in the middle, the 1, 2, 3, 4, fifth joint. Now this joint looks relatively bad. I can still see the pad where my joint needs to be connected to. It doesn't look like the solder has very good connection with the soldering element there with the pad. And it also looks like the soldering liquid does not make a very good connection to the board. Now, what does that tell me? It told me that as I did my soldering, as I was soldering my component to my board, I got bored or distracted because the first one is good. The second one, yes. Third one, okay, also good. Fourth one, starting to get a little bit weird. And then the fifth one, I was bored. I don't know what happened, but I did not make a good connection. Now, in testing, this actually works. So I test the board, it does work. But as I'm using or physically handling the board, I might move the component and that component then moves, and then the weaker joints like that will break. And this one did break. So you will have to look at your components, how they are attached, how they are soldered, and then also see where you would have bad joints, and then you'll probably need to redo those joints. Now back to the screen, and you probably see that at this joint here, I realized, oh no, I've made a mistake, or these joints are not look so good anymore. And then I started probably again after a little bit of rest, and the next joint looks good. Now as well, you might see that this it looks like there was some sort of liquid that's on the board itself. That is something we call flux. Now, flux is a material that you use alongside of with your solder. So flux is a material that adheres to your metal circuit, and it just enables your soldering fluid, your soldering metal, to adhere more easily to the components that we'd like to adhere it to. A lot of the soldering, or when you do soldering by hand, the flux is contained within the soldering metal itself, or a lot of the times you will put on the flux separately. So you will coat your elements that you would like to solder with flux. And then when you melt your soldering metal, it adheres to the elements which you would like to adhere to be more easily. But usually you'll clean your board with an alcohol wipe or an alcohol disinfecting wipe, and then wipe away the flux. But because I was a student and didn't want to, I left the flux on there. Now, flux is not electrically conductive. It just conducts heat. So leaving the flux on there is not really a problem because it does not create a short between my circuits. But what might be a problem is that it is thermically conductive, meaning that it conducts heat. So wherever the flux is over a wide area of my circuit, if one component creates a lot of heat, that is then shared throughout the board, and that might create some issues. So whenever you have a board like this, give it a good wipe with usually with some sort of alcohol-based wipe. Sorry, I just have to do something. And that usually just cleans away the flux. But like I said, I was a student, I didn't know, or either I didn't want to, but you can still see the flux Here you can still see the flux. And like I said, it is not a huge issue, but then also the flux can relay some thermic, some thermal elements. Okay, so I'm going to show you a couple of other joints as well, where I made not the greatest joints in the world. Specifically here. Now that is not a very good soldering technique. You can see that I have, there is way too much soldering liquid here. This joint here is shorting with another element here. That pad, I've put on so much soldering liquid on there, so much soldering elements on there that it overflows the pad and it connects it to a connection which it should not make. So this is very much a bad situation. And here you can see everywhere there's too many blobs of my soldering liquid. And that is usually a very, very bad sign. And that might have the effect of shorting my soldering iron, my circuit, and create bad, unnecessary connections. And this is something that you will also be aware of. Now, what happened here? How does this happen? Well, once again, I got a little bit lazy or I got rushed. Sometimes the soldering iron does not work as well as you would like to. A lot of the times the soldering iron, the tips you will have to clean quite often because the impurities in either the soldering iron itself or the impurities of the board, they get melted and burned onto this tip. So you would have to clean it quite often to make sure that it conducts heat very well as well. A lot of the times the soldering irons have got very, very sharp tips so that it transfers the heat to a very, very small surface area because some of these components are really, really small. So what often happens is that at the tip where you are pressing the soldering iron to your component, that becomes dirty. How did it become dirty? Well, the soldering liquid that you are melting, those have some impurities in them, and those impurities then collect on the soldering iron. And then what happens is at that tip, the soldering iron does not conduct the heat as well anymore. So you're pressing the soldering iron to the component and then pressing the solder to the component, and it just does not melt. And you're sitting there and it doesn't melt. What's happening is the tip is dirty and not transferring energy. So what you do, I move the soldering liquid up the tip because the whole tip is warm, and it starts melting at the top. And then it creates a little blob, and then that blob flows down and then flows onto your circuit board and creates some of those blobs right there. Now, it does create a connection, yes, but it's not a good connection because the soldering is not a very good, it doesn't adhere to the circuit itself or the component. It just sort of like encases the through-hole component in a big blob of soldering liquid or, well, liquid metal. It still makes a connection, but it's a very weak connection and it breaks very easily. And added to that, it creates this blob, and that blob might be so big that it overflows and shorts out other circuits. Now, here you can see that effect, the blob running down. It does make a connection, but it makes also a connection here. And you can see here, this whole area here, I should have cleaned my soldering iron and I should have redone all these connections. Now, what do you do if you have made an error like this? Well, you have these little suction pumps that you press in. You heat up the soldering liquid again. You press a small button and it sucks out the liquid, it sucks out the soldering, and then cleans it quite easily. It's relatively easy to fix this. I didn't, but my board still kind of worked to some extent. It didn't work exactly like I wanted it, but it still works. So whenever you create a design and you will have to test the design, remember that sometimes it is not your design that's a problem. Sometimes it is the physical attachment through soldering of the components. And it is something that you will have to be aware of that might happen or might affect you. It's not necessarily you. It might be the connection itself, or I'm just. It might not possibly be you, but it might be actually the connection itself. So whenever you have, whenever you're testing a board or receiving the board, you have to do a visual inspection, look over the board, these microscopes are quite common in PCB designers' offices. You will see them scrutinizing the board, looking over all of the connections, and then realizing like, that is a bad connection. I should redo that. Now I'll look at a more professional board. This is an Arduino board with lots of surface mount connections, and all of these connections I think were done with machines. And I'll show it to you. I'm sharing my screen again. So this is just a close-up of the IC, or the main chip of the board. And here you can see it's a surface mount chip, and all of these connections are exceptionally well done. So these are surface mount components, and as you see, these are the traces running beneath my solder mask, and these are incredibly well-made joints. You can see this is a button, a surface mount button, and as you can see there, the attachment there is pretty much perfect. On the back side with the through-hole components, as you can see, these are almost perfect connections. The soldering liquid covers the whole of the pad and also the whole of the protruding element, and it is just really perfect. So how do all of these perfect connections get made? Well, these are mostly made with a machine. How does a machine do this? Well, you'll have your board placed onto the machine without the components. It will have, through the design, your PCB design that you have created, you will create a map for where it will need to place specifically little blobs of soldering liquid. So we'll place the little blobs wherever it needs to be, wherever you have these surface mount components. And then the next step, it will take the surface mount components and place it directly on these little blobs. It will then subject the whole board to a heat within a small oven. And then the surface mount component will then sink into the those little solder blobs that you have placed on the board. making a near perfect connection. The same thing for the through-hole components. The components will be pushed through these blobs, also within the oven, and then that will create all the connections sort of like at once. So industrial boards usually do not use soldering irons. We will use these machines that will place all of these blobs automatically, place your components on top of these little blobs. So it's little, a blob is just a very, very small amount of the soldering paste in this case. So paste, it's more a malleable, looks like a clay form of solder, and your component then inside of the oven, which heats up the whole board to just the temperature for the melting point of the paste. All your components just simply sink into it and creates almost a perfect connection. So there's one other board that I would like to show you. This is an RFID reader board. So what it does is you've got these little tags. You place the tag on the board. It reads the signal between this tag and the board can then send information to your little board. But what is interesting, I don't know if you can see this, is that it has got, no, you can't, I'll show it on the microscope. It's got a an inbuilt antenna. Well, most of your, well, not most of it, all of the wireless elements of a, if you have any sort of wireless communication with any of your boards, you will have to have some sort of antenna. Even your mobile phone, if you have a wireless functionality in your project, then you will have some form of antenna. Now, a lot of the times, these are physical antennas that you screw into the board and you'll see them sticking out. But a lot of the times, the antenna is embedded within the board and usually with a sort of like a trace. So I'm sharing my screen once again. Here are a row of surface mount capacitors. On the one side, you have this line, another line, and that in actual fact is the antenna. So the antenna for this surface mount board, it runs on the perimeter of this, through this board, and it runs along the perimeter on the outside of this board, and that is your antenna. So the antenna that picks up the signal being sent from this tag is a trace, is a normal trace, nothing special about it, but it is just an embedded within the board itself. So the antenna is within the board itself. So it is another thing that you will need to think of if you have a wireless application and it needs an antenna. You can also create that within your PCB design and have something that looks like this, where you have the antenna of your board on the outside or anywhere on the inside, and create your antenna itself. So traces are a very, very, very useful element, and not only can they carry voltage or current, whatever, or a signal, they can also be used as antennas. And a lot of the times, these if you're dealing with a wireless application, you can embed your antenna inside of the board as well. So the word I just used, embedding, means that you have something inside of something else. So I embedded my antenna into this board, and that antenna is then integral to the board. I do not need to have anything else antennas that I need to screw in. And a lot of more modern design uses this idea of embedding your antenna into so like that board. So what was my idea behind showing you this? It is another step in printed circuit board design, is that you will have to inspect your design. Like I keep on telling, the prototyping process is something that you will have to deal with if you are designing these products. So you will then start with a schematic, which we'll have a look at in a minute, and then do a simulation, create a prototype, usually on a breadboard or some sort of temporary physical circuit, and then move on. If that design is validated or passes your test, then it moves on to your printed circuit board. But as you move on in this process, you will also have to add in more tests and validation. And one of those validations is looking at the physical appearance of the board and also the physical connections that was made through the soldering process or attaching the components to your board. And that involves, it's not limited to, but it as a component of that is the visual inspection, where you physically look at the connections that you have made. Is the electrical connections fine? Does the soldering iron does the soldering liquid make good connection with the component and also the trace it's supposed to be connecting to? Are there soldering liquid that makes shorts between the two layers? And another thing, which is not such a big problem with these types of boards, because the traces are covered within resin. So if you do have, sometimes we have splashes of soldering liquid where you press the soldering iron, the soldering liquid to the iron may be too warm. The liquid might have like a very, very small explosion where it just like pops away. And then those little soldering bubbles falls onto your board. And that, in terms of this board with so like the exposed elements, might cause shorts or unintended connections. So you will have to inspect your board, see if the connections are made, are they good? If they look suspect, or if they look like they do not make good connections, then I always recommend redoing them. And usually redoing them is not a big issue. If you just take the soldering iron, reheat the joint with the soldering iron, the solder melts. Usually that melting process then also creates a better connection. So usually it's pretty easy to fix these elements, and also using a device that might remove the soldering liquid once you have once you've identified an area where there's too much soldering liquid. Now, unfortunately, this class is not a practical class. It would be great if it was. I might see if I can have a board where I attach a couple of elements with a soldering iron, make some mistakes and tell you what that looks like. But then I'll probably have to have another camera, because this one is not really that great. It's good for looking at individual joints, yes, but it's not really good to look at the process. But I'll see if I get that working, because that is something that's interesting. And that's also something that's part of the PCB designing process. Now I've run a little bit out of time. Unfortunately, I wanted to show you Eagle quite quickly. I'll probably do that. I'll have to do it in the next class, unfortunately. Usually what happens if I do something and I'm quite excited to show it to you, then I tend to talk too long about it. But don't worry, the next class, which I think is on Wednesday, I'll send the link straight after this class is done. We will then start with the Eagle programming. But hopefully we will have enough knowledge now to just continue on with using the Eagle software. And we should have, yeah, it'll be fine. We will continue with it, and hopefully by the end of it, you will all be relatively good at using the Eagle software. So, as a recap, so this class, we looked at all of the theory that we handled in last week, and then also I showed you some practical examples of like visual inspections of printed circuit boards. And that is part of the validation testing part of the design. So not only does your board need to pass like electrical tests, now electrical tests can involve, now the testing process for a lot of companies are different. There's no real set specification. There might be in your company, but what I'm talking about more is that your circuit is designed to deliver 5 volts to a certain area or to a certain pin. So when you are testing, you will take a multimeter or an oscilloscope or something or other device that can indicate voltage across a certain element, and then you can measure that voltage across that point, and it will, then you can test if it's 5 volts or not. So that's like the testing which I mean in this case. And then it not only needs to pass, so like, does it deliver my expected voltage, but then you also look at the physical joints itself and inspect the joints itself. Now, as you build up more experience with things like this, you will become better at identifying bad joints. But usually if the joint looks bad, there's too much soldering iron, so much soldering liquid on it, or if it looks cracked or damaged, then you'll probably have to redo the joint. And as we spoke about, sometimes the joint, if it does not make a good connection, if the component moves, it will start to break and crack and then lift up from the board itself. And that in the initial testing probably won't come up because there is still a very good connection, or not a very good, but a connection made between the component and the circuit. But then as the board gets used more and more, that connection will break up. But then it is relatively easy to identify those sort of like broken joints. And like I said, I will try and show you a practical example of a board and a short demonstration on soldering. And then hopefully I can show you how a good soldered joint should look like and how a bad solder joint is made. But that will all happen in future classes. On the class on Wednesday, we will then start directly with EagleCAD and jump into the schematic creation of our PCB boards. And then also we'll start with simulation. And then the week after that, we will create more, we will create our first printed or PCB design. And then after that as well, we will then create more advanced PCB designs. So it should be very, very, very exciting. Once again, if you have any questions, if something you didn't understand something, if I mentioned something and it's you think like, well, that doesn't make any sense, please contact me, send me an email, have your class representative send me an email. have the teaching assistant send me an email, but just let me know. Even if you do not understand some words that I am saying or the language I'm using, just let me know. Right. So I don't want to start with something new because we've only got about 4 minutes left. I'm going to end the class right here. I'll send you the link to the next class right now. And then, yes, also remember, install EagleCAD. Make sure you have some sort of access to the program somewhere, because I will require you to create your own circuit designs, especially for the final exam, project exam. So you will need to have the free version of Eagle installed somewhere, or access to somebody who has it installed, because you will have to use the software and create a printed circuit board to be able to pass this course. But that being said, thank you for tuning in to this class. I will see you all on Wednesday. Have a very good rest of your Monday. See you on Wednesday, and then we'll jump straight into using EagleCAD. Right. Have a good day. Bye, everybody.